just equilibrium problems, kind of how we saw how we had K constants that would tell you to what degree something would react. It's the same thing with weak acids and weak bases. The only difference is we used KEQ to talk about the equilibrium constant, and we used KC to talk about concentrations. KP was using partial pressures of gases. Now we call it Ka, and that's just the equilibrium constant of an acid. It's the exact same thing. Your Ka is always going to be your products over your reactants. Leave out solids and liquids. So here we go. For weak acids, what we're trying to do is relate the pH and the Ka and the molarity of the weak acid. Those are the three things we're relating. Let's see, we already saw the strong acids were the easy ones. For the weak, we'll use this equilibrium thing. We're going to set up our initial change in equilibrium concentrations, so a table just using molarity. The initial concentration is going to be the concentration of the acid before it dissociates. And the pH is telling you the equilibrium concentration of the H plus that you measure after the acid dissociates. So this will be your I in your ICE, and this will be your E in your ICE. So let's get the pH of a 1.2 molar hydrofluoric acid, and we're given the Ka. So we'll do the same thing that we used to do with equilibrium problems. Write the equation, set up the ICE table, write the K expression, and start solving for stuff. So I've got hydrofluoric acid. With weak acids, take the weak acid, put it in water, and you'll see that we know, I'm going to do this equilibrium arrow because it's weak. We know that weak things give, or acids give up an H. So I'm going to go ahead and put that, or take off the H. So I'm left with this, here's the weak acid, here's the conjugate weak base. And then I'm putting the H right here on the water. So I have H3O plus hydronium ion. Okay, so that's my equation. This is a liquid, so I'm going to leave this out, but all the other things are aqueous, so they'll be involved in my K expression. I'll look at my initial, my change in my equilibrium. Initially, that's the concentration of the acid. It was 1.2. Okay, so I have this solution that was 1.2 molar. I am assuming that I start off with none because it's before it's dissociated. Then I have my change, some amount dissociates. And for every 1 mole of HF that dissociates or splits into 2, I make a mole of this. So this will be plus X. Minus X here, plus X here, plus X. So I'm left with X of fluoride and X of hydronium. So then I write my K expression. I know Ka is going to be products over reactants. So concentration of fluoride times concentration of hydronium divided by concentration of hydrofluoric acid. So Ka is equal to 7.2 times 10 to the negative 4th, and that's equal to this times this, x squared over 1.2 minus x. And we know that, actually we get to do a little trick here. I can say that since my initial molarity is 100 times larger, it's more than 100 times larger than the Ka, I'm allowed to assume that this x is going to be so small that 1.2 minus x is really just 1.2. So I can say this doesn't really matter. Okay. So now I'm going to multiply, I want to get this x by itself. I'll multiply both sides by 1.2. And, show my word. Oh, I didn't. I'm going to multiply both sides by 1.2, and then I'm going to square root both sides. So I end up with 1.2 times 7.2 times 10 to the negative 4th is equal to x squared. So then I'm going to square root this side, and I'll square root this side. If I square root x squared, I just get x. So that's my x, 1.2 times 7.2 to the negative 4th, and that is equal to 0.02, 939, and x, these problems are so long, sometimes you solve for the x and you don't even know what you solve for. Well, you just solve for the amount of fluoride and the amount of hydronium. We're looking for pH. pH is the negative log of the concentration of the hydronium, so we're going to use this x to get that. So pH is the negative log of the concentration of the H plus or of the hydronium. It's the same thing. So I'll just go ahead and plug in negative, or I'll just plug in 0.02939. when I typed that in, I found out that the pH was equal to 1.53. Let's see, with that I have 2 sig figs, and this has 2 sig figs, and this has 2 sig figs. Because remember, with pH, it's after the decimal is significant. Done. So next, I'll calculate the pH. This time I have a weak base. So the equilibrium expression of an acid is Ka. The equilibrium expression of a base is Kb. And it's the same thing, products over reactants, but you just happen to be using a base. So we take our weak base, it's ammonia, that's NH3. You put the weak thing in water, and oops, water is H2O, and you find out what happens. So bases take on an H+, so that means I'm going to be left with ammonium ion, and I made some hydroxide. Okay, so I'll go ahead and set up an ICE table. What do I have initially? What's my change? What's my equilibrium? And initially I have 0.5 molar of the ammonia. I don't care about water, it's neutral, and I assume that there's none of that. So then I'm going to say I have a minus x, so 0.5 minus x, and I'm left with x of this and x of this. So my K expression, this time it's Kb. Kb is equal to 1.8 times 10 to the negative fifth, and that's going to be this times this divided by this. Products over reactants, there's no coefficients, so everything's 1. So that's going to be x squared over 0.5 minus x. Okay, and I have the same thing going on here where I can say that this is at least 100 times smaller than this, so I can assume that x is going to be really small. I can assume that it's going to be so small that 0.5 minus x is really just 0.5. I should check that later, by the way. I didn't on the last one, and that was bad. So then what I'm going to do, I'm going to multiply both sides by 0.5, so 1/2. Now I have 9 to the negative 6. So after I multiplied this side by 0.5, I got rid of this. Multiply this by 0.5, I get that. That's equal to x squared. I'm going to square root both sides and square root that. So I'm left with x is equal to that. So x is equal to 0.003. And then what I'm going to do is I just solved for the x, and I can see that x is this guy. So x is hydroxide. It's also this. This isn't really going to get me any closer to the pH, though. This will. From that, I'll get the pOH, because I know that pOH is equal to the negative log of the concentration of the OH, and that's my concentration of the OH. So 0.003. So that means my pOH I get is 2.52. And I know that 14 minus pOH gives me the pH. So that's 11.48. And I got 2 sig figs and 2 sig figs and everything. So that's it. At this point I should go back and I should check. I should make sure that when I plug in this x, that x squared divided by 0.5 minus x really is close enough to this. So I will check that and make sure before I would end the problem.